So welcome everybody. Today our speaker is Hongguang Liu, so from Erlangen University. So Hongguang finished his PhD in Marseille. So it was joint Marseille and Paris under supervising of the Karim Noui and Alejandro Perez. And now he's a postdoc in Erlangen. So Hongguang, you can start your talk.
Yeah, thanks for the introduction, and thanks to our organizer giving me this opportunity to present the work at this seminar. So as you can see, the topic of today's talk is improved effective dynamics of loop quantum gravity black hole and the Nariai limit. We will relate effective dynamics from the loop quantization of the symmetry reduced model. And you can see the Nariai limit arrives as a solution after the bounce, and we remove the singularity inside the black hole. And this work is in collaboration with Mu-Xin Han, and here is the archive number. So this is the outline of today's talk, well, or a summary of what we have done. So we propose a new model of the spherical symmetric loop quantum gravity black hole in the loop quantization or polymer quantization, and we derive the effective dynamics of this. This model comes with infinitely many degrees of freedoms, namely it is the 1 plus 1D field theory. And then we study the effective dynamics of both interior and exterior of this black hole. We show that the classical limit is recovered in log curvature regime, namely they recover the Schwarzschild space-time. And also on the high curvature regime, the black hole singularity is resolved, and it is replaced by the no singular bounce. After the bounce, the evolution stabilizes asymptotically to the charged Nariai limit, which is ds2 cross s2. And then we study the possible black hole evaporation and the quantum tunneling effect around this charged Nariai limit, and this propose a scenario of the black hole to white hole transition on this charged Nariai limit. And finally, we show that this charged Nariai have much more interesting physics behind, because it has infinite zero modes quantum degeneracy, and this can be viewed as an example of Wheeler's bagel God. Bagel God. So here is a brief introduction of our formalism. So we start with the reduced phase space formulation. So the reduced phase space formulation is we couple gravity and standard matter field to clock field at classical level. So we use this clock field to deparametrize the gravity variables such that it provide a physical time and physical space variables. So here we use Gaussian dust to deparametrize the model. And this action is the classical action for this Gaussian dust model. And it was introduced by Kuka and the collaborators, and also studied by Thomas Tima and Christina in their paper. And this field, this energy momentum tensor of this dust action can be viewed as a heating conducting dust fluid. That's why it's called a dust. And here T and S are clock field, and rho and W are Lagrange multipliers. And then after you couple this system to gravity, and you deparametrize the gravity variables with the value of dust field, where you view this T as physical time variable and this sigma as, this S as physical space variables. And then you can show that the gravity now becomes, the deparameterized gravity now have Dirac absorbers and physical Hamiltonians because of this dust field. So we study it still in a loop quantum gravity style. So we study the gravity Dirac absorbers as SU2 hashtag Barbero connections, and also the SU2 value, the densitized triad, which is SU2 value, the electricity flux of the gravity. And these two now are gravity Dirac observables on the physical time and physical space, which marked with tau and sigma. And they follows the following Poisson bracket or the canonical relations, and all the other brackets are zero between them. And from here, we can define the physical Hamiltonian. The next property of this Gaussian dust is that the physical Hamiltonian only involves the scalar constraint. And the vector constraint becomes a symmetry, and it will not enter the physical Hamiltonian. And the physical Hamiltonian in the A and E variables can be written in this way. This is the scalar part, and this is the vector part. Remember, after the deparametrization, the vector part becomes a symmetry instead of constraint. And the classical equation motion is simply given by the usual Hamiltonian equations with this physical Hamiltonian. Sorry, this H should be C. And now we apply this framework to black hole space-time, so mainly the spherically symmetric space-time. So this means we now write our dust space variables, which is now R cross S2, which have the spherical symmetry. Now the coordinate, we chose it to be x, theta, and phi. And the Gauss constraint, we solve it with gauge fixing. So the gauge fixing is chosen such that the electric field is diagonal. So this is the value of this electric field on the coordinate. And then you can also solve out for A, for the connection field, and it proves that it will be written in this way, which given already studied a lot by previous papers. And on this gauge fixing, you can show that the symplectic structure is now given only by the by the Poisson bracket between Kx and Ex, as well as K phi and E phi. And Kx, Ex, or K phi and E phi, they are all canonically conjugated variables, and you only have these two. And the metric is given in this form, where lambda is given by E phi over square root of Ex, and R is given by square root of Ex only. And you can show that if you don't like the Hamiltonian formalism, you can also derive the Einstein equation directly from this metric form, and you'll see after you perform then the Hamiltonian analysis, you end up with the same canonical structure. And then you can show that, so with this metric, the physical Hamiltonian can be written in this way, where this is some very simple calculations. And as we said, now the vector part, after the deparametrization, they become a symmetry. And actually, they have infinitely many conserved charges from this from the previously vector constraint. And now it's a special diffeomorphism symmetry. And this introduces infinitely many conserved charges. But now, if this Cx is 0 when you choose the initial condition to make this Cx to be 0, then the Hamiltonian density is also conserved. So this defines a 1 plus 1D field theory at classical level, which contains infinitely many degrees of freedom. So this is already different from many previous loop black hole models, which they mostly study the homogeneous part, which is the canonical sex models inside the horizon. Now we can briefly introduce the solution of this space-time. So the general solution of the equation motion is the so-called LTB space-time, the Lemaitre-Tolman and bounded space-time. And this is the general solution to the general form of the solution to the metric. One important thing is that the Schwarzschild solution is given by the limit with where the dust energy density goes to 0. And then you can say when dust energy density goes to 0, this Rx can be solved with fx can be chosen as x. So if you replace it, you'll get the Schwarzschild solution in terms of this LTB metric, which is the constant, which is n is chosen to be 1. And when this x is equal to t, this is the place of the classical singularity. But one important thing is when we go to this limit, somehow we break the deparametrization because we need dust field to deparametrize the gravity model. But this is only happens at, this is the classical level, I would like to say. And then we'll go to the quantum level. This is just, we just write out the improved Hamiltonian at this level. So as usual, what happens in loop quantum cosmology, we do not quantize, we do not regard this k phi or kx as the operator, but we make the exponential of them to be an operator. This defines the quantization on the line, which is on the bar compactified lines, would like to say. And we also introduce a so-called mu-bar scheme regularization, which this is notation in loop quantum cosmology, I would like to say. The mu-bar means now this part, the regularization inside the sign is related to the metric field or to the electric field. So basically the regularization is make a polymerization of the connection field. And this all the extrinsic field, if you want, in this context. And we just make k phi to be a sign of k phi and kx to be a sign of kx. This comes from, as I said, to regard the exponential of kx or k phi as an operator instead of regard themselves to be operator. And this square root of delta are fixed area to every placket, and usually people related it to the minimal area gaps in loop quantum gravity. And after we do this regularization, we can show that the effective physical Hamiltonian is given by this way. It's actually only exactly given by send of k phi to the function of k phi and kx to the function of kx. So because of this sign function, well, it's basically related behind is the SU2 symmetry introduced by the hashtag connection and the electric field. So this Hamiltonian, this sign function will effectively give a bound to the extrinsic curvatures, so it removes the singularity. And we'll see later this is exactly what happens by numerics. And also this is only an effective physical Hamiltonian, but I think but you can show that if you study the quantization of this model, you get exactly this effective physical Hamiltonian from the quantum Hamiltonian at zeroth order level. And my collaborator Hongguang, I think, is working on this. So this physical Hamiltonian have a boundary term if we want to derive the equation motion, and the boundary term can be written in this way. And the boundary condition we chose to evaluate this equation motion is we impose asymptotic flatness, which is Schwarzschild boundary conditions at x goes to infinity or x is very large. And actually you can show this boundary condition is 0 in that way. So we can ignore the boundary condition on that part. And on another part, which is x goes to minus infinity, we impose the Newman boundary condition, which is ex prime goes to 0 as x goes to minus infinity. And you can show that this boundary condition still to be 0 at minus infinity. So we can ignore both by our boundary conditions. The nice thing of this framework is if we don't modify Cx, the spatial diffeomorphisms, they are still conserved with this improved Hamiltonian. So this will finally lead to the notation of the infinity remaining zero modes on the Nariai geometry. We'll see this later. But one thing I want to mention is that since this Vx is still conserved, but the Hamiltonian density, they do not be a conserved charge even when Cx goes to 0. They are not a conserved charge anymore, which means that the dust density can change during the evaluation. So now we will study the effective dynamics of this model. So we can derive the equation motion from this effective physical Hamiltonian. As you can see, since this is a 1 + 1D field theory, you get nonlinear partial differential equations for the canonical for the phase space variables, and the equation motion for Ex larger than 0 and Ex smaller than 0, they are related by space-time inversion, and in this way. But this nonlinear partial differential equations is very difficult to study. First of all, you need to impose some no-trivial initial values on the whole cursive slice if you want to evolve the system, but we don't know at this moment. So we study a more simple case, which we introduce a new variable, z, which is equal to x minus t. And you can see before in the Schwarzschild solution, which is the limit when dust energy goes to 0, is exactly only depends on this z. This somehow, introducing this z is introducing some stationary solutions or introduce some extra symmetry in this space-time. And you can regard this z parameterizes spatial slice when fixing t, or it parameterizes the time evolution when fixing x. In terms of Schwarzschild solutions, this is the signature of the time translation symmetry in the outside Schwarzschild black hole somehow, or the homogeneous inside the horizon. You can regard this condition like that. And under this condition, this nonlinear partial differential equations become a linear, sorry, it's still nonlinear, but it becomes first order ordinary differential equations, which is more easy to solve. And then we can impose the initial values at z equal to 0, which is very large than 0. And the initial value we give is the asymptotic flat. As we said, we also use this boundary condition. You can regard. So this is the asymptotic flat Schwarzschild spacetime, which given by this one in terms of z. And remember, for z equal to 0 is a singularity for these Schwarzschild solutions. But we'll see later this singularity will be removed. So now we come to the actual numerical evaluation to study the property. So as we said, we begin with the Schwarzschild initial condition or the Schwarzschild boundary values. And this numerical value is given with these parameters, which is not important, but one thing I would like to say is just that we are very far away from the Schwarzschild singularity. And also we study the very large black hole, which RS is chosen to be large. RS is the black hole mass of the Schwarzschild radius, if you want. And this is the result. So you can see that when z is very large, the solution, the Christman, this is a plot for the curvature scalar. And when z is very large, we can show that it approaches the Schwarzschild solution. And even at the horizon, it also approaches to the Schwarzschild solution. There is no quantum, there is very tiny quantum corrections to this. And then at what to be the singularity, the Christman becomes large, but it's bounded. So you remove this singularity at what is supposed to be at equal to 0, but then the curvature scalar goes smaller again, and then there is a second bounce happens, which is become larger again. And after that, the solution stabilized at ds2 cross s2 geometry. Here is just the zoom out of these two bounds, the place of these two bounds happens. And you can see they are oscillating behavior, but they are all bounded. One remark I would like to say, because we use dust to deparametrize the model, but you may ask, because the Schwarzschild solution doesn't have dust energy density, why you can use this Schwarzschild solution to evolve this? The reason is that, as I said, the physical Hamiltonian density is not a control charge. So now it will change during the evaluation. And even we start with this Schwarzschild solution, but it will also comes with some very tiny modifications. You can see this comes from the numerical error or something else, but this is like the evaluation with very tiny initial dust energy density. And then after the evaluation, the energy density will grow, and it will peak at this at the first bounce, and it will becomes large, and then it becomes small again. And for the DS2 cross S2, it becomes 0, which removes the dust. But this DS2 cross S2 is already the stabilized or the end of the evaluation of this universe. So that's fine for us. And also we study the null property of this space-time, and this is the null expansion. And you can see that this quantum effective, the effective theory of this physical Hamiltonian doesn't change the position of the black hole horizon. At least they only give very tiny effect which cannot see from this plot. So which means that the quantum corrections at the black hole horizon, they are negligible. And also this are the local curvature maxima, the plot of these two local curvature maxima at different bounds. So we have two bounds here. And if you plot the maxima values of these two curvature scalars, two Christmas scalar with delta, they are both a function as 1 over delta square. So that they are, so this is a proof that they comes from the quantum effect. If you regard delta as the minimal error gap which introduced by loop quantum gravity, or a regulator introduced by UV. It's a UV cutoff if you regard it thermal. So, and then we move to the DS2 cross S2 region on the leaves at c equal to minus infinity. So you can see that when the solution approaches c equal to minus infinity, this E5 will grow exponentially, but EX will stabilize at R0 square. And this part actually, under this assumption, when E5 goes to asymptotically, you can even write out the linearize the equation motion for E5, when E5 is large, or you can, which you can expand the equation motion in terms of 1 over E5, for example. And then you can show that this solution, the solution is exactly the solution for that equation motion. And this finally lead to a DS2 cross S2 metric, which is written in this way. And this R0 square of this stabilized the EX is the S2 radius. And this alpha 0 is the, this is S2 radius, and this alpha 0 is the DS2 radius, which relate to the effective cosmological constant. And alpha 1 is another parameter which depends on the initial value. Both R0 and alpha 0, they doesn't depend on this on the black hole mass, and they are Planckian. So which means and also we also study the perturbation, and the perturbation shows that both R0 and alpha 0 they are stable under perturbations, but alpha 1 is not. So basically, perturbations will change alpha 1, but doesn't change alpha 0 and R0. So they stabilize to the same DS2 cross S2 geometry, because alpha 1 you can always perform a redefinition of the x, for example, redefinition of the coordinate to absorb it into dx. So this alpha 1 are something related to the spatial diffeomorphism in this space-time. Moreover, we show that this R0 and alpha 0, they are both depends on the UV cut of delta. And here is the plot for different initial values for different deltas, I would like to say. So you can see that it doesn't depend on the initial value RS, but it linearly depends on the square root of delta. So they are both quantum effect. You can understand this effective cosmological constant arise from the quantum effect or this UV cutoff. This is very similar if you are familiar with what happens in the unsymmetric bounds from loop quantum cosmology. They are very similar to that, where there is also the theta space-time, but that's only the theta. It's not ds2 cross s2, which the theta space-time happens after the bounds. So as I said, this alpha 1 non-linearly depends on both initial values and also square root of delta. And this quantums, we can introduce a quantum state if we want on this ds2 cross s2 or the quantum Nariai geometry, because this is the metric for the charged Nariai geometry when this s2 is not equal to the ds2 radius. So if you introduce a quantum state will be labeled by R0, F0, and alpha 1. So this state will depend on alpha 1. So this means you have an infinite degeneracy on the same geometry. And this infinite degeneracy is lead to the Wheeler-Spiegelgard interpretation. And actually it is due to the spatial diffeomorphism symmetry, because we still have the spatial diffeomorphism symmetry in the improved Hamiltonian. One thing I would like to mention is similar geometries are also found in Kardashev-Sachs black hole interior models, but they have some drawbacks. One important thing is that in the previous studies, the mu-bar scheme model of these black hole interiors produce large quantum effect near the event horizon. Even when the horizon is very large, means even they are in the low curvature regime, they still produce very large quantum corrections. But for Earth, the quantum corrections at black hole horizon, they are very tiny, they are negligible for large black hole horizon. And then the second thing is area of the S2 part. In the previous studies, it becomes smaller than the minimum area loops, than the minimum area gap delta at certain stage of the time evolution, which means their model is inconsistent with the mu-bar scheme treatment of these holonomies, because you already impose this delta as the minimum area gap you can achieve. But for us, we show that well only by numerical investigations, all the possible initial value we test, we always have this S2 area larger than square root of delta. So we are free of these problems. And this is the whole space-time diagram we obtain. So we start with the Schwarzschild boundary condition of the Schwarzschild initial values, and on the part when the curvature is low, we are still very close to the classical space-time. So this S is a typical space slice with constant t, if you want. And this is also can be regarded as the slice with those evolution, if you want. So this part, they are still classical. And then when you approach the classical singularity, you are enter the quantum region, which the curvature becomes Planckian, but they are bounded. And then after you bounce several times, actually you bounce 2 times, and then you end up with a complete future infinity, which is a charged Nariai geometry in this space-time. As I said before, we also performed the linear perturbations with certain initial values, and we found that all those linear perturbations are bounded from above. And one important thing is this charged Nariai geometry. They are stable classically under the perturbations. But one thing is that they may be unstable quantum mechanically. And this will give the opportunity for the quantum tunneling between different Nariai geometries. And I'll show this later. Another thing is we also study the average null energy condition from the classical effective energy momentum tensor. And we can show that it is violated. And this violation is true because you give modifications to the Hamiltonian, or which means you give modifications to the Einstein equations, which remind you need to redefine the effective energy momentum tensor. So, and this violation is inspired truly by the loop quantum gravity effect, or the modification of the Hamiltonian, if you want. So with this diagram, we would like to study the black hole evaporation process. So for the evaporation process, since we study the stationary black hole, if we want, in the previous studies using this constant Z and the constant Rs. So if we take into account the back reaction from Hawking radiation, we are considering some near static process, which we consider some approximations with slowly shrinking horizon. Sorry. And then in this slowly shrinking horizon, each constant t zero surface. So with each constant t0 surface, we have a different Rs, which is slowly shrinking. And then we can solve each t0 by solve the effective equation motion again, which means that this dynamical black hole horizon, which is slowly shrinking, can be approximated by a large number of spatial slices. They carry different solutions with different Schwarzschild radius. And this Schwarzschild radius is monotonically decreased as t grows in. So this is the idea to approximate the dynamical horizon and to take into account the Hawking radiation. And then this is the result. So here, these 4 plots are different for the different decreasing Schwarzschild radius. I don't know if you can see clearly the value of Schwarzschild radius. This one is 10 to the power 5, and this one is 1000, this one is 10, and this one is 0.19. And you see when the Schwarzschild horizon is decreasing, these 2 bonds, they become closer, and suddenly they coincide with each other at this smallest value of this Rs. But as we said before, the Nariai geometry is invariant under changing Rs, and they're independent of Rs. So these asymptotic geometries are always the same under Z goes to minus infinity part. But what changes is these 2 bonds. And when the 2 numbers become closer and closer, and then suddenly they coincide with each other, there may be a domain war, because you directly separate the Schwarzschild solution on the other hand and the DS2 cross S2 on the other hand. Sorry, the Schwarzschild solution on one hand and DS2 cross S2 on the other hand. And actually, we also plot the null expansion of this scenario, and on this smallest possible Rs, and you can see why we call it the smallest possible Rs we can have. So this is what happens when this N0 and smaller, so these 2 bounces position, they coincide with each other. You see here, now we don't have a trapped surface anymore, because this the supposed to be a horizon becomes the transition surface, and they change the value of both theta k and theta l for the ingoing and outgoing null expansions. And then there are marginally anti-trapped. There are another marginally anti-trapped surface and the transition surface again. Actually, there's some oscillation inside. But as you can see, since you remove since there is no trapped surface anymore, the Hawking radiation process breaks here. So this is when Is is really small. This means you're already going to the quantum region. So due to this very strong quantum effect, the trapping dynamic horizon disappears, and the Hawkins derivation of evaporation fails. And in this regime, we may need the force theory of loop quantum gravity, or we may need a nice quantization of the effective model to describe what is really happening here. One remark I would like to say is in all this derivation, all the area we can produce is still larger than the minimal error gap we impose. So this analysis is self-consistent with this mu bar scheme we imposed. So with this evaporation process in mind, we can now study the possible black hole to white hole transition. So as we can see, there is some cutoff of the Hawking radiation. When you have a minimal Schwarzschild horizon, you can produce when the Hawking radiation stops. And then you can ask what happens after. So to see what happens after, we need to extend the space-time we studied before. So first of all, we need to extend the region which take into account all these Hawking radiations. And this region is what we call this ST tilde. Under asymptotic geometries, they need to be coincide with each other. What we impose is the ADM mass are approximately the same under region 1 and this under the Schwarzschild part and also region 1. So this is basically the procedure we use to derive the effective dynamics. As I said, near this classical geometry region, which is the spatial infinity, we will approximate this by quantum field theory on the classical background time or the flat Schwarzschild background time, asymptotically flat Schwarzschild background time. And this dynamical effect is very weak near this R0, so we can. So then we, for all the spatial slices in region 1, we approximate their asymptotic geometries using classical asymptotically flat geometries. And also we impose the condition that their geometries are continuous extension from these geometries in the past. So what means in this procedure is that we ignore the back reaction from Hawking radiation because we don't consider the change of the ADM mass. So this is the gluing condition in this extension. So for the space-time on the past, on the Schwarzschild, we have the T and X in this way, which is increasing T means decreasing or this RS, and you have different slices here. But this new foliation on this part need to be introduced, and actually you can show that they are related by time reflection symmetry, as you can see from the two plots. And these are supposed to be these are the t squared minus x squared equal to 1, and this one is t squared minus squared equal to minus 1 in the future. And under this time reflection symmetry, the gluing condition for EX and E phi are given in this way, where EX becomes minus EX and E phi is the same. And this gives us new boundary conditions for the classical equation motions on this region 1. So in the future of this Schwarzschild solution. And under this new boundary conditions, we can now also solve the equation motion. And actually, if you remember before, I introduced some space-time inversion symmetry of the equation motion. Actually, this one can be solved exactly by this reflection symmetry given before. And it produces a white hole solution, which is anti-trapped region on this region 1. And one important thing is it produces another charged Nariai geometry, or DS2 cross S2 geometry. We call DS2 cross S2 tilde. And this tilde is different from the previous DS2 cross S2 because they have opposite curvature signatures. But even they have the same E, but they have opposite curvatures, so they cannot simply glue together. But this is also This is also the reason. This is also due to the reason that DS2 cross S2 is itself a complete null space-time. So future space-time. So it is itself is complete. So you can go to the infinity of this space-time. So which means we may need some quantum tunneling to make the transition possible from this region to this region on the quantum region. And there are some evidence for this effect. So if we write out the improved Hamiltonian density at these two charged Nariai geometries, remember this sorry, there is a typo. Remember this reflection symmetry, which you sent the extrinsic curvature to minus the intrinsic curvature. You can see this. You can see that the improved Hamiltonian density is invariant under this symmetry. So which means that for these two Nariai geometries, they have the same Hamiltonian improved Hamiltonian density. And actually on the DS2 cross S2, this density is 0. So this density, if you plot the property with K, they are double Ward effective potential for K, which means that for given value of rho, you have two values of K, which separated by a potential wall. And this is very similar to the quantum tunneling effect in quantum mechanics. And another reason behind is, as we said before, in this quantum charged Nariai geometry, the EX is stabilized, which means its conjugate momenta Kx fluctuations need to be very large in quantum mechanics level. So there are possible quantum tunneling between these two geometries. And this is our argument for this possible black hole to white hole transition. But of course, to understand what really happens, we need a quantum theory for this space-time. And finally is a remark for this infinitely many infrared states. So as we said, this energy density in the charged Nariai geometry is 0. And we also see before there are infinitely many states which have the same R0 and alpha 0, but they have different alpha 1, which means all the states in this spacetime, they are infrared states, they are soft, which means they are soft modes, and they are infinitely many, because it's alpha 1, you have infinitely many alpha 1 generated by the action of spatial diffeomorphisms. So this gives an example of Wheeler-Spiegel's God. So this action of diffeomorphisms can be regarded as changing alpha 1 to alpha 1 prime. So which means the Hilbert space of this DS2 cross S2 geometry is a representation space of the group of one-dimensional diffeomorphisms. And this may be some quantum theory behind. For example, you can relate, we can use the weight algebra or the Wilsonian algebra if we allow the central charge to describe this Hilbert space. If we regularize them on a circle, for example. Yeah, that's all what I want to talk. I'll end up with some outlooks. As we see, there are mainly 3 parts or 4 parts of what we still need to be done in this work. So we need to study what really happens from the black hole to the Nariai limit, and what happens between these two bounces, and what happens between what happens inside the horizon. There will be so for example, we can study the thermalization predicted from this effective Hamiltonian, and we can study what's the relation with Hawking radiation and what corrections it may give for the Hawking radiation. And then near this Nariai limit, we need a detailed analysis of the quantum tunneling, and we also need a detailed analysis of these soft modes, the infinitely many soft modes on this geometry. And then from the black hole to white hole transition, we also need to study what is the transition beyond the effective theory, and what happens with this quantum chaos, with this quantum the quantum perturbations on this space-time. And all these three studies need a quantization of the effective Hamiltonian, which is the ongoing project. And the end thing is, since we use a very tiny dust energy, is good to see what happens when we use large dust energy momentum density to start the evaluation and to study even for the dynamical collapse. And this is important. This is very important since we use the deparametrization model or reduced phase space model, where you need a dust energy and momentum density finally to deparametrize the system. And thanks all.
So thank you very much for the nice talk. So now we have time for questions, I think. So
can I ask 2 questions?
Yes.
Okay, so first of all, I would like to say that it is very nice work, and it's very balanced. That means that you not only did the calculations, but also looked at the limitations, which is very nice and not so common nowadays. I have 2 questions regarding essentially the connection of semiclassical and quantum regime. So first of all, you have this, I'm sorry for my pronunciation, Nariai limit, right?
Yes.
Which normally, if you wouldn't have the tunneling, would be some kind of remnant, if I understand it correctly.
In this case, I think we don't have remnant. You have remnant in the Euro case for this Nariai geometry.
Okay,
where,
okay.
Yeah.
Anyway, I don't want to go too much into it. What I want to ask is, at some point you define the effective potential for tunneling.
Yes.
For defining this effective potential, you are essentially using semi-classical approximation, this effective dynamics.
Yes.
On the other hand, for the tunneling itself, you need already quite large fluctuations, large second-order quantum corrections.
Yes.
And the problem is that in order to derive the quantum effective dynamics, you essentially set them to 0. And in this region, essentially what I want to say that the very fluctuations you need for tunneling will also modify your well. So I'm afraid some extension to the theory, to the effective dynamics may be needed to have really better control over probabilities, over what really happens there. It is very nice heuristic picture, but to have it, let's say, in a reliable manner, you need to include higher order quantum corrections, even within the model, because of course, full theory corrections you mentioned will modify it again. But even within this model, the quantum elements will affect, and potentially even in a qualitative way, if we are unlucky, the outcome.
Yeah, I agree. Yeah, there may be also corrections to the potential. Yes.
And another thing is you postulated the effective dynamics using mu bar scheme, which is very common, very good. Thing is that it is heuristic, let's say, postulate. And we have right now a couple of works which tries to construct the semi-classical analysis out of full theory. So have you maybe compared, related somehow to those works to sort of verify this particular prescription, whether it is consistent or, well, or full theory considerations people did may give something different?
For the black hole, they are very less. I think they are very less.
Yeah, there are maybe 2 papers, I'm afraid. So
for the cosmology, there are a lot, I think.
Yeah, but there are these papers by Dapor, Asanyusi, right? They tried to look exactly at this very problem, how to arrive to the classical dynamics. So normally, I have to say, these postulates work very well in practically all models we managed to verify. They were the right assumptions, but would be nice to have verification whenever it is applied in a new domain.
Yeah, I agree. But the force theory is, well, if you really start from the force theory, there may be more things we need to do.
Oh, yes, of course. But these hopefully would be corrections, right?
Yes,
I'm talking about leading order results.
Well, some taste from how you start from the force theory. I think if you start from the force, well, this work is like you start from the force theory and you study only the continuum limit of the force theory, for example.
Oh, yes.
This is the continuum. Yeah. And then you give some UV regulator to the force theory, and then you study its continuum, I guess.
Yeah, the problem is that, for example, Martin can come and say, yeah, you are choosing wrong regulator. That should be,
Okay, yeah.
That's why I ask for possible, say, external verification of this.
Yes, I agree. We me and Muxin, we also have a paper, but not on black hole, but on cosmology recently, I think on January. We also propose a way to give effective dynamics from the force theory, from the force theory coherent state path integral.
Okay.
But it's on cosmology, and we reproduce, but it's not exactly the mu-bar scheme because we use dynamic lattice for that theory, and then it can reproduce a theory very similar to the mu-bar scheme, but it's not exactly the same.
Well, I will be disappointed if it reproduced exactly mu-bar scheme because
it's not exactly the same. It's not exactly the same, but actually it captures all the properties of this mu-bar scheme. So it means
that's at least that's good.
No, it's not the same. The reason is that we use coherent state path integral, so we don't modify the Hamiltonian, but we modify the equation motion somehow. Because this equation motion are coming from the dynamical refinement of the lattice. So you cannot, so there's some, for the Hamiltonian part, you have some no regulated curvature terms or something like that.
And you have plans of applying it to this model, maybe?
Yeah, I think we are planning also to do that.
Okay, that would be great. Okay, then thank you very much. That's all from my side.
So are there other questions?
So I would like to ask about this Nariai metric. What is special about this metric? How did it happen that it appeared this place? Is it static or it doesn't look static? So
it doesn't static. It's a constant cosmological. You have a constant cosmological constant on DS2, and then you have a S2 part, which is sphere. So this part is the cosmological constant, and this part is the sphere, which is you always have
just sphere. So this is time dependent model, yeah?
Yes, this is time dependent.
So how it could be end state of anything if it is time dependent?
It depends on your. I think it depends on your viewpoint how to describe this geometry, because in any case, this geometry is only labeled by 2 parameters, or if you want by 3 parameters, right? You only have R0 and alpha0 to identify the geometry. That's why we write the quantum state above it to like this way.
But why are you saying it is time dependent? Actually, de Sitter is also can be viewed as time dependent.
I don't
So
know, but
I think it has time-like killing vectors in some regions, or it doesn't. So dt plus dx seems to be a killing vector. I'm not sure what is its norm. Probably depends on the values of those parameters alpha 1 and alpha 0.
you can write it in this null coordinates, yeah, easily. What then? But there will be a factor, yeah, in front of the.
Yeah. So,
but this is
so
just
this
the
metric.
product.
So this metric is obtained by a limit from the limit from extremal Schwarzschild de Sitter.
Yes.
Right. Oh, I see. So the yeah. So extremal Schwarzschild de Sitter actually doesn't have time-like killing.
Oh.
And does it have extremal horizon, or is horizon not in this domain? So
No, it's not in this domain.
Yeah, I think those coordinates, they don't cover this. So
no, but you have there is this retarded coordinate. The retarded coordinate tends to -infinity, so it could be scry minus. Yeah? No, time, yeah, -infinity. I see.
But can I understand correctly this symmetric? So is it just a product of two-dimensional de Sitter with two-dimensional sphere?
Yes.
So it's geodesically complete. So there is no boundary of this space. So
yeah,
how it can be connected to this outer part?
Well, you only have this solution on the z goes to -infinity part. So this is
okay, so you're just cutting part of that.
Yeah, we take only part of this.
Okay, yes. So now I understand. Okay, so no, so then the horizon is this boundary that you cut out.
But they are dynamically. I mean, you are dynamic. You are away from this one, but there's no really boundary for this because this comes from the, for example, the numerical evaluation of this system. Everything is so you are approaching the geometry close, and until they go to -infinity.
Okay, so it's modified. So it's never this Nariai space exactly.
Yeah.
Okay.
It's only the limit when they go to -infinity, but it's never.
And on this Penrose diagram, where is it? That -infinity is scry minus, yeah, or what?
No, but square minus is Schwarzschild for this space-time.
So where is that equal to -infinity?
It's here, this point. This is z equal to -infinity, and here is z equal to +infinity. And the Schwarzschild end, the usual Schwarzschild metric end with z equal to 0. And this is here is the classical singularity. Well, this is maybe the drawback of this RTB space-time coordinate, because it's a bit. So here is z equal to -infinity, and here is z equal to +infinity, and here is z equal to 0, which is the classical singularity.
But if time tends to infinity, you don't go to scry minus. There's something that I don't understand in this combination of signs.
Well, because how to say? Because in this coordinate, you can change the rule of the evaluation between time and between your time coordinate and your space coordinate.
Yeah, I think that time is what we usually denote by r. So this is r going to. infinity is cry.
Yes. Yes.
I have a more general question. So in your results, there are two scenarios. One is that we have tunneling. So the second result is tunneling black hole, white hole, and the first possibility is this which you discuss here. So what makes this transition from black hole to white hole?
So
when transition from black hole to white hole happens, and when it doesn't happen, what does it depend on?
Well, it's for me, it depends on the here. So it also become coming from this black hole evaporation process. So when you approach this minimal, this minimal RS you can have when this trapping dynamic horizon disappears, you are in a very high quantum. You have very strong quantum effect, and then there are some suddenly quantum region happens. So quantum effect happens, and then so it's exactly at this corner, for example, at this corner where the black horizon is comparable to the Planckian radius, for example. The Schwarzschild radius is comparable to the Planckian radius, and then you have a strong quantum effect, and then you may have some jump between or quantum tunneling between these geometries. And inside the horizon, the jump is the jump between the Nariai geometry, because in this case you see this bounce is like a domain where it separates directly the Schwarzschild and the DS2 cross S2. Yeah.
So which case is more likely to happen?
So
are black holes more likely to explode as white holes, or are they more likely to become Nariai spacetime?
No, but the Nariai spacetime is always behind. I mean, when you go inside the black hole, you always end up with, I think, in this spacetime. When you go inside the black hole, you always end up with this Nariai geometry, and this Nariai geometry you may jump inside. But when you stay outside and you see what happens to this black hole under evaporation, and then you will see this black hole evaporate, and then it suddenly jump to a white hole. I think that's the picture.
Wojtek, przepraszam, może ty zakończ seminarium, a najwyżej rozmawiać dalej.
Yes. So maybe let us finish official part. So thank you very much again for the nice talk. So I will stop recording.
Okay, you're welcome. Thank